Hey everyone, and welcome to this explainer. Today we're diving deep into the invisible physics that literally govern our modern hardware. We're specifically breaking down the math and the mechanics behind mutual inductance and magnetic coupling. My goal here is simple. We're going to take those dense, complex engineering principles right out of the textbook and translate them into practical, real-world intuition that you can actually use in your designs. Let's get right to it. To give you a quick roadmap of how we'll break this down, we're going to start with a real-world hook so you can see exactly why this matters. Then, we'll cover the atomic concept, walk through the actual math step by step, tackle a concrete example problem, look at a massive gotcha that trips up tons of engineers, and wrap up with the key takeaways.
Okay, first up, the real-world hook. We're talking electromagnetic interference.
I want you to imagine this scenario. You've just designed a flawless circuit. The logic is perfect, the power delivery is absolutely solid. But the second you power it on, your perfectly routed signals just start corrupting each other. You're getting data errors, jitter, weird phantom glitches. You're probably sitting there wondering, why is this happening? Well, the answer lies in an invisible invader.
Just look at the incredibly complex environment of a modern printed circuit board. You've got hundreds of closely packed traces, multiple layers of copper, and signals firing back and forth at lightning speed. Here's the thing. Whenever current flows through any of these traces, it generates a magnetic field. And because everything is packed so tightly together, that magnetic field from one trace literally reaches out across the board and induces a voltage in a totally adjacent, completely unconnected trace. This is the root cause of magnetic crosstalk, and it is exactly why mastering mutual inductance is absolutely non-negotiable for hardware engineers.
So let's zoom in a bit and look at the atomic concept behind this, magnetic flux. Let's clearly define our core term here. Mutual inductance, which we denote as M12, is the magnetic flux, or phi12, penetrating a second circuit divided by the current, I1, flowing in the first circuit that actually produced that flux. Just like equation 210 from our source text states, when current in circuit 1 produces a flux in circuit 2, that exact ratio is your mutual inductance. It's essentially the literal measure of how much one circuit's energy is invading another circuit's personal space. If the math is starting to feel a bit abstract, I want you to use this visual analogy. I actually call this the never forget rule. Picture a totally calm lake. You drop a stone into the water. That stone, that's your source current, I1. The water ripples that radiate outward from the splash represent the magnetic flux, phi. Now picture a small boat floating just a little bit away. As those ripples travel outward and hit the boat, it starts to rock. That rocking motion is the induced voltage in circuit 2. So mutual inductance is really just measuring how big the initial splash was and how hard it ultimately rocks that nearby boat.
Okay, so to calculate exactly how strong those ripples are by the time they reach the boat, we rely on the Biot-Savart law. That equation is B equals mu times I, all divided by 2 pi r. Let's break those variables down really quick. I is the current, which is our stone. R is the physical distance that the ripple traveled to reach our boat. And you'll notice that R is in the denominator, meaning the further away you are, the weaker that magnetic field gets. Makes perfect sense, right? Finally, mu is the permeability of the medium itself. You can think of mu as the thickness or the density of the water that's actually carrying those ripples.
All right, moving on to section 3, deriving the math for mutual inductance. We're going to build this piece by piece so you never get lost. The structural logic here requires 3 exact steps. First, we calculate the magnetic flux density, B, using that Biot-Savart law we just talked about. Second, we integrate that density over an area to figure out the total coupled flux, phi12, that is actually hitting our victim circuit. And finally, step 3, we just divide that total flux by the source current, I1.
Let's see this in action with section 4. A walkthrough example using nested coplanar loops.
Take a really close look at the specific geometry we have here. We've got an outer loop made up of conductors 1 and 2, and that's carrying an interfering source current, I1. Now, sitting right inside it is a nested loop. This is our victim circuit, made of conductors 3 and 4. If you look at the cross-section spacing at the bottom, you'll see the distance from conductor 1 over to conductor 3 is labeled A, and the distance from conductor 1 all the way across to conductor 4 is labeled B. So let's execute step 2 of our math plan and find the actual flux crossing that inner loop. We're going to take our Biot-Savart equation and integrate it across the empty space from distance A to distance B. That gives us the integral of mu times I1 divided by 2 pi r with respect to r. And as you might remember from calculus, when you solve that integral, the 1 over r simply becomes the natural log.
So the flux from conductor 1 alone is mu times I1 divided by 2 pi, multiplied by the natural log of B over A.
But wait, we're not done yet, because we have two conductors in our source loop. Because this specific geometry is perfectly symmetrical, conductor 2 is pushing an absolutely equal amount of magnetic flux into the inner loop and in the exact same direction. So what do? We simply multiply our previous result by 2. That 2 in the numerator perfectly cancels out the 2 in the 2 pi denominator, so our total coupled flux, phi12, simplifies to mu divided by pi times the natural log of B over A, all multiplied by I1.
Finally, we hit step 3. We find our mutual inductance, M, by dividing that total flux by the source current, I1, which means the I1 term simply drops right out of the equation. Next, we substitute in the standard constant for the permeability of free space, mu, which is 4 pi times 10 to the negative 7th henries per meter. When we plug that constant in, the pi in the numerator and the pi in the denominator perfectly cancel each other out, and that leaves us with this beautifully clean, elegant equation. M equals 4 times 10 to the negative 7th times the natural log of B over A. And boom, that is exactly how you calculate the mutual inductance for a nested loop.
Now, let's pivot sharply to section 5. This is the gotcha, and we're talking about magnetic shielding. I want you to take a really close look at this setup. Let's say you're doing your math, and you realize your mutual inductance is way too high. So you decide to place a non-magnetic tubular shield, labeled S here, entirely around your victim conductor. Then you ground that shield, safely assuming it's going to block all those magnetic ripples. But does it actually work? Let's check out the equivalent circuit over on the right.
Okay, here is the brutal engineering truth that trips so many people up. Grounding a non-magnetic shield at one end does absolutely nothing to stop magnetic fields. I repeat, it has zero effect. Why? Well, because a shield grounded at only one end doesn't form a complete circuit, so it cannot flow any current. It's basically just acting like an antenna, not a cancellation loop. If you want to fight magnetic fields, that shield absolutely must be grounded at both ends. Only then can the induced voltage inside the shield actually flow as a physical current, and it's that current which creates its own opposing magnetic field to cancel out the incoming noise.
And this perfectly illustrates our golden rule of shielding, which is equation 2-21 in the source text. It states that the mutual inductance between the shield and the center conductor is exactly equal to the shield's own self-inductance, or, simply put, M equals L sub S. Because the shield current is totally uniform around the outside of the cylinder, there is literally no magnetic field from the shield current existing inside the cavity itself. Therefore, a countercurrent flowing through a shield that is grounded at both ends perfectly couples to the inner trace, effectively neutralizing all of that magnetic interference. It's a real game changer when you get it right.
All right, bringing it home with section 6, a quick summary and our final takeaways.
Number 1. Always remember the boat analogy. Mutual inductance is simply the ratio of those magnetic ripples hitting your circuit divided by the current that caused the splash in the first place. M equals phi over I. Number 2. For nested coplanar loops, all that intimidating math elegantly simplifies down to M equals 4 times 10 to the negative 7th times the natural log of B over A. It is heavily dependent on your geometric spacing. And number 3, our massive gotcha, a non-magnetic shield grounded at only one end provides zero magnetic protection. You have to ground it at both ends to allow those countercurrents to flow.
Understanding how to master and control these invisible fields is exactly what separates good hardware engineers from great ones. If you found this deep dive valuable, be sure to hit subscribe for more EMC and automotive communication protocol survival guides right here. But before you go, I want you to think about those physical distances, A and B, on your own circuit boards. How are you routing your most sensitive traces today? Let that sink in, and I'll see you in the next one.